Let us start with F-test and chi-square test. What is F-test? F-test was discovered by G.W. Snedeker in agricultural experiments. The performance of a treatment is assessed not only by its mean but also by its variability. Hence, it is of interest to us to compare the variability of two populations. In testing up hypotheses, the equality of variances, the greater variance is always placed in the numerator and the smaller variance is placed in the denominator. While we testing through the F-test, by F-test we test the two variance ratio, and F-test is used to test the equality of two population variances, equality of several regression coefficients, ANOVA, etc. The range of F-test is 0 to infinity. F-test is always having values greater than 0, that is larger variance divided by smaller variance, always having values greater than 0. That's why F-test having always greater than 0 values. Let x1, x2, xn1 and y1, y2, yn1, yn2 be two independent random samples of sizes n1 and n2 respectively drawn from two normal populations which are independently normally distributed with mean mu1 and variance sigma square, and second sample y1, y2 up to yn2 is independently normally distributed with population mean mu2 and population variance sigma 2 square respectively. S1 square and S2 square are the sample variances of the two populations samples. Then null hypothesis H0 such that sigma 1 square is equal to sigma 2 square, means both the population variances of both the populations are same from where the samples were drawn having sample variances S1 square and S2 square. Under the null hypothesis, the test statistics becomes f is equal to larger variance divided by the smaller variance, and f is equal to s1 square upon s2 square, where s1 square is greater than s2 square, which follows f distribution with n1 minus 1 and n2 minus 1 degree of freedom, where s1 square is equal to 1 upon n1 summation of x square minus summation of x ka whole square upon n1, and s2 square is the sample variance of second sample, that is 1 upon n2 minus 1 and summation of y square minus summation y whole square divided by n2, and f is equal to s2 square upon s1 square, where s2 square is greater than s1. If s2 square is greater than s1, then we place s2 square in the numerator. If s1 square is greater than s2 square, then we put the s1 square in the numerator. Larger variance F-test is equal to larger variance divided by the smaller variance, and which follows a distribution with if f is equal to s2 square upon s1 square, if s2 square is greater than s1, variance of second population is greater than variance of first population, then it follows f distribution with degree of freedom here changed, that is n2 minus 1 and n1 minus 1, while here f is equal to s1 square upon s2 square. S1 square is larger than the s2 square because s1 square is having larger variance and s2 square having a smaller variance. That's why we put the s1 square in the numerator and s2 square into denominator. In this situation, f distribution having degrees of freedom, numerator degree of freedom is n1 minus 1 and denominator is n2 minus 1, and here we see s2 square is larger than s1 square and s2 having degrees of freedom n2 minus 1 and s1 having degrees of freedom n1 minus 1. If calculated value is f is less or equal to table value of f at n2 minus 1 and n1 minus 1 degree of freedom at a specified level of significance, then the null hypothesis is accepted, and we conclude that the variances of two populations are homogeneous, otherwise they are heterogeneous or are said to be H0 said to be non-significant and H1 will be accepted. This is the table value of F at 5% level of significance. These are the numerator degrees of freedom and these are the denominator degrees of freedom. And if we have to find out if we have 5, n1 is equal to 5 and n2 is equal to 10, then n minus 1, that is 4, and n2 minus 1, that is 9. 4 and 9 is 3.63 will be the F tabulated value at 4 and 9 degree of freedom. If S2 square is greater than S1 square, then we see here S2 is 9 here and S1 is 4 here. That is 6.00. That is the value of F at 9 and 4 degree of freedom, while 4 and 9 degree of freedom, the F value, table value is 3.63. These are the values of F at 1% level of significance. Example, the heights in meters of red gram plants with two types of irrigation in two fields are as follows. Tap water 3.5, 4.2, 2.8, 5.2, 1.7, 2.6, 3.5, 4.2, 5.0 and 5.2. In saline water 1.9, 2.6, 2.3, 4.3, 4.0, 4.2, 3.8, 2.9 and 3.7. Test whether the variances of two systems of irrigation are homogeneous. Let us start solving this problem. First, we establish the null hypothesis at 0. The variances of two systems of irrigations are homogeneous. And alternative hypothesis H1 is the variance of two systems of irrigations are heterogeneous. And that is sigma 1 square is equal to sigma 2 square, means both the population variances are same. Under H0, the test statistic F is equal to S1 square upon S2 square, that is S1 square is greater than S2 square, and where S1 square is the first samples variance, that is 1 upon n1 minus 1 summation of x square minus summation x whole square divided by n1, and S2 square is the second sample variance, that is 1 upon n2 minus 1 summation y square minus summation y2 square upon n2. We calculate the sample mean and sample variance. This is the x variable and this is the y variable. X variable having summation x 37.9 and summation y is 29.7. Summation x square is 156.35. These are the square of 3.5 square is 12.25, up to 5 square is 25, and these are the y square. 1.9 square is 3.61 and 3.7 square is 13.69. That is summation y square, that is 104.33. First, we calculate S1 square is equal to 1 upon 9, that is 10 observations, that is 10 minus 1 is 9, and this is summation x square and this is summation x whole square divided by 10, and that is 1.41 meter square, and S2 square, that is 1 upon 8, that is number of samples are 9 here, n2 minus 1 is 8, and summation y square is 104.33 and summation y is 29.7 square divided by, after solving we get 0.79 meter square. That F is equal to S1 square having larger variance, S2 square having a smaller value, so that the larger variance divided by smaller variance, that is 1.41 divided by 0.79, that is 1.78. This is the F calculated value. Table value of F 0.5 for n1 minus 1, n2 minus 1, that is 9 and 8 degree of freedom, that is 3.23. Here we see that the calculated value of F is less than the table value at 5% level of significance. Hence H0 is accepted, and we conclude that the variances of two systems of irrigations are homogeneous. Let us take a second example. Two random samples drawn from two normal populations are sample 1 20, 16, 26, 27, 22, 23, 18, 24, 19 and 25. Second sample having values 27, 33, 42, 35, 32, 34, 38, 28, 41, 43, 30 and 37. Obtain the estimate of variance of the population and test 5% level of significance whether the two populations have the same variances. Let us start solving the problem. Null hypothesis first we establish H0 so that mu sigma 1 square is equal to sigma 2 square, that is the two samples are drawn from the two populations having same variances. And alternative hypothesis, that is H1, that is sigma 1 square is not equal to sigma 2 square, that is two-tailed test, and x1 bar is equal to summation x1 upon n1 and x2 bar is equal to summation x2 upon n2, that is x1 values, these are 1 2 3 4 5 up to 10 values, and these are the y are the 12 observations, that is x1 values x1 minus x1 bar, subtracting 10 22, that is x1 bar is 22 and 22 is subtracted from 20, that is minus 2, 16 minus 22 is minus 6 and so on, and we have x minus x bar is 0, this is the property of mean, and x1 minus x1 bar square, that is 120. Second variable x2 or y, we take here the having values 27, 33, 42, 35. These are the 12 observations, that is summation x2 or summation y is 420 and x2 minus x2 bar or y minus y bar, that is 0, and y minus y bar or x2 minus x bar square, that is 314. This is x bar is 22 and y bar is 35, that is they are also designated as x1 bar, x2 bar. Level of significance is 0.05. The static f is defined by the ratio of f is equal to s1 square upon s2 square, where s1 square is equal to summation of x1 minus x1 bar square divided by n1 minus 1, that is 13.33, and s2 square is summation x2 minus x2 bar square upon n2 minus 1, that is 314 divided by 11, that is 28.54. Here we see that this s2 square, yeah, or the variable y or x2 having the larger variance, while the s1 square variable x having a smaller variance, so that we change this formula and we have s2 square upon s1 square, that is 28.54 divided by 13.33, and having follow n2 minus 1 and n1 minus 1 degree of freedom, that is 2.14. This is the calculated value of f, and expected value or table value of s2 square upon s1 square follows a distribution with 11 and 9 degree of freedom, that is 3.10, and here we see that the calculated value of f is less than table value. Here we see that we draw the inference, since f calculated is less than f tabulated, we accept null hypothesis at 5% level of significance and conclude that the two samples may be regarded as drawn from the population having same variances. Means two samples drawn from the population having the same variances. Example third. The following data refer to yield of wheat in quintals on plots of equal area of two agricultural blocks A and B. A was a controlled block treated in the same way as block B except the amount of fertilizer used. Block A, block B, number of plots are 8 here, number of plots are 6 here, mean yield is 61 and here mean yield is 51 and variances are block A 50 and block B 40. Use F-test to determine whether variance of two blocks differ significantly or not. Here already given n1 is equal to 8, n2 is equal to 6, x1 bar is 60, x2 bar is 51, s1 square is 50, s2 square is 40. Here s1 square is greater than s2 square, and null hypothesis which we established here, h0 is equal to sigma 1 square is equal to sigma 2 square, that is there is no difference in the variances of the yield of wheat. And alternative hypothesis, h1 sigma 1 square is not equal to sigma 2 square, that is two-tailed test, and level of significance is 0.05. Calculate the test statistic by this f, And what is S1 square? That is N1 S1 square upon N1 minus 1. That is 8 into 50 divided by 7, that is 57.14, and S2 square is equal to N2 S2 square upon N2 minus 1, that is 6 into 40 divided by 5, that is 48. Since S1 square is greater than S2 square, then 57.14 divided by 48, that is 1.19. What is the tabulated value or expected value? And this is the FE for expected or tabulated, that is S1 square upon S2 square, follows a distribution with 8 minus 1 7 and 6 minus 1 5 degrees of freedom, having table value is 4.88. Here we see that the calculated value 1.19 is less than 4.88. Since F calculated is less than F tabulated, we accept the null hypothesis and hence infer that there is no difference in the variances of yield of wheat. Both the plots having same yield. Uses of F-test for equality of two population variances. दो समष्टियों के प्रसरणों की समानता जांचने के लिए F-test is used for the significance of an observed multiple correlation coefficient. अवलोकित बहु सहसंबंध गुणांक की सार्थकता जांचने के लिए F-test is used for significance of an observed correlation coefficient. अवलोकित सहसंबंध अनुपात की सार्थकता जांचने के लिए F-test is used for testing the linearity of regression. समाश्रयण गुणांक की रेखीयता जांचने के लिए F-test is used for equality of several means. बहुत से माध्यों की समानता जांचने के लिए to test the significance of observed partial correlation coefficient. अवलोकित आंशिक सहसंबंध गुणांक की सार्थकता जांचने के लिए. These are the uses of F-test. Let us start with chi-square test. Chi-square test for testing of the goodness of fit. Carl Pearson in 1900 developed a test for testing the significance of the discrepancy between experimental or observed values and the theoretical or expected values obtained under some theory or hypothesis. This test is known as chi-square test for goodness of fit and is used to test if the deviation between experimental or observed, जिसे हिंदी में प्रेक्षित एवं theoretical और expected अपेक्षित frequencies कहते हैं. Under the null hypothesis that there is no significant difference between the observed and expected value. This is the null hypothesis for testing with chi-square. And chi-square is equal to summation of I from n. OI means observed frequency of ith value minus expected frequency of ith values square divided by expected frequency and then their sum, that is O1 minus E1 square upon E1 plus O2 minus E2 square upon E2 plus up to On minus En square upon En. It follows chi-square distribution with n is equal to n minus k minus 1 degree of freedom, where O1, O2, On are the observed frequencies and even E2 up to En are corresponding to the expected frequencies, and the k is the number of the parameters to be estimated from the given data. A test is done by comparing the computed value with the table value of chi-square for the desired degrees of freedom. Here that is n minus 1, here k is 0, that is there is no restriction, that is n minus 1. Let us take an example. 1000 students at college level were graded according to their IQ and the economic conditions of their homes. Use chi-square test to find out whether there is any association between economic condition at home and IQ. These are the conditions of the students: rich, poor, and their level of IQ, high and low. Rich students having 460 students having high IQ, while 140 having less IQ. Poor student 240 students having high IQ, while 160 students having low IQ. And this is the row total, that is 460 plus 140, that is 600, that is R1. This is 240 plus 160, that is 400, that is R2. And this is the column total, 460 plus 240, that is C1 and this is C2, and this is the total frequency, that is capital N. Null hypothesis. We establish first null hypothesis. There is no association between economic condition at home and IQ level of the students, and both are independent. Expected value of E11, that is expected value of 460, is equal to 600 into 700 divided by 1000. Here we see that is A and B. 600 into 700 divided by 1000, that is 420, and E12 expected frequency of 140, that is can be obtained by subtracting the values of 600. After subtracting 420 minus 600, we get the 180, and if we subtract 4 to 0 from 700, we get 280, and if we subtract 180 from 300, we get the 120. These are the sum of the frequencies, and these are the expected frequencies. Observed frequencies are 460, 240, 140, 160, and expected frequencies are 420, 280, 180, and 120 respectively. Then O minus E square, that is 460 minus 420 square, that is 40 square is 1600, 240 minus 280, that is minus 40 square is 1600, 140 minus 180, that is minus 40, that is 1600, 160 minus 120, that is again 40 square, that is 1600, and dividing each by expected frequency, that is 1600 divided by 420, that is 3.81, 1600 divided by 280, that is 5.74, and 1600 divided by 180, that is 8.889, and 1600 divided by 120, that is 13.333. If we take the sum of these chi-square values, that is 31.746, and chi-square observed is equal to summation OI minus EI square upon EI, that is 31.746, and this is the table value, that is expected value of chi-square distribution with 2 minus 1 into 2 minus 1. There are 2 rows and 2 columns, that is R minus 1 into column minus 1, that is 1 degree of freedom, that is 3.84. And here when we compare the calculated with the table value, here calculated value is greater than the table value, that is chi-square observed or chi-square calculated value is greater than chi-square tabulated or chi-square expected value. Hence the hypothesis is rejected at 5% level of significance, and there is association between economic condition at home and IQ level. As we established the null hypothesis that there is no association between economic condition and IQ level of the students, but after calculation of chi-square, we see here that the calculated chi-square is 31.746 and tabulated value is 3.84. Calculated value is greater than the tabulated value, that is H0 is rejected and H1 is accepted, which shows that there is association between economic condition at home and IQ level of the student. Example, a cross between two varieties of sorghum, one giving high yield and other for high amount of fodder was made. The number of plants in F2 generation were observed is 79, 160, 85. Test whether the sample data is in agreement with the Mendelian ratio 1:2:1 or not. ज्वार की दो प्रजातियां, एक अधिक उपज देने वाली तथा दूसरी अधिक चारा देने वाली किस्मों के बीच एक क्रॉस किया गया। F2 पीढ़ी में पौधों की संख्या 79, 160, 85 के रूप में प्राप्त हुई। जांचें कि क्या नमूना आंकड़े मेंडेलियन अनुपात 1:2:1 के साथ समझौते में हैं या नहीं। First establish H0. The sample ratio is in agreement with 1:2:1, and these are the observed frequencies 70, 160, and 85. Total frequencies are 384, and expected frequency we find out through this formula, that is total frequency 324 into 1/4, 1/4. because they are ratio in 1 raised to 2 raised to 4, that is 1 by 4, 2 by 4 and 1 by 4. That is 1 by 4 of 324 is 81, and once expected value of 160 is 324 multiplied by 2 by 4, that is 162, and expected frequency of 85 is equal to 324 multiplied by 1 by 4, that is 81. That here we see that 81, 162 and 81 are the expected frequencies. O minus E is 79 minus 81 is minus 2, 160 minus 162 is minus 2, and 85 minus 81 is 4. And squaring is 2 square is 4, minus 2 square is again 4, and 4 square is 16, and 4 divided by 81, that is 0.0494, 4 divided by 162 0.0247, and 4 divided by 81, that is 0.1975, that is the sum of all chi-square values is 0.2716. Since chi-square calculated 0.2716 is less than chi-square tabulated 5.991 with 3 degree of freedom at 3 minus 1, that is 2 degree freedom at 5% level of significance, therefore the null hypothesis is accepted, and we conclude that the plants are segregating according to the Mendelian ratio 1 raised to 2 raised to 1 in F2 generation. Now we are taking 2 by 2 contingency table for testing independence of attribute. Chi-square is a measure of actual difference between expected and observed frequencies, and such if there is no difference in expected and observed frequencies, the value of chi-square is 0. chi-square वास्तविक और प्रत्याशित आवृत्तियों के अंतर का माप है, अतः दोनों के मध्य अंतर नहीं होता है तो chi वर्ग का मान 0 के बराबर होता है. Suppose a 2 by 2 contingency table having 4 cells and having in the row, these are the two attributes of a sample or any testing things, that is two attributes, and both having two situations or two conditions or two classes. They are A, B, C and D. These are the row total R1, R2, and this is the column total C1 and C2. This is a 2 by 2 contingency table, and R1, R2, C1, C2 denotes the row totals and column totals, and N denotes the total number of frequencies. Then chi-square can be directly calculated by this formula: N into AD minus BC square, A into D multiplied minus B into C whole square divided by A plus B, C plus D, A plus C and B plus D. In other words, we can say that chi-square is equal to N, the total number of frequencies, in the bracket A into D minus B into C whole square divided by R1 into R2 into C1 into C2. With degrees of freedom, there are 2 rows and 2 columns, that is 2 minus 1 into 2 minus 1, that is 1 degree of freedom. Let us take an example. In an orchard of 750 trees, a record was taken of the number of shaded and unshaded trees, and in each of these classes the frequency of high and low yielding tree was noted as below. These are the shaded and unshaded plants, and low yielding were 640 and low yielding in unshaded were 05, while high yielding in undershaded in shaded condition 510 and unshaded 295. Test whether shading on the tree has an effect on its yielding capacity or not. हमें टेस्ट करनी है कि इनमें yielding capacity में शेड का कोई इफेक्ट है या नहीं. These are the two attributes, high yielding and low yielding, and these are the two conditions, shaded and unshaded. We have to test whether these are independent or they are having some association. By chi-square using 2 by 2 contingency table, we find out the solution of this problem. First, we establish the null hypothesis. The shading on the tree has no effect on its yielding capacity, and H1, that is alternative hypothesis, the yielding capacity of the tree is affected by the shading. These are the data of 640 low yielding under shaded condition, and unshaded condition the yield is 305. High yielding gave yield in shaded condition 510 and unshaded condition 295. The total are 945, that is A plus C, A plus B, and C plus D is 805. Here A plus C is 1150 and B plus D is 600. That is R1, this is R2, this is C1, this is C2. Putting the value in the formula chi square, that is calculated, equal to n into A into D, that is 640 into 4 295 minus 510 into 305 whole square divided by 945 into 805 into 1150 into 600 divided by, after calculating these values, we got 3.686. Square of this AD minus BC square. Table value of chi square at 1 degree of freedom at 5% level of significance is 3.84 and the calculated value is 3.686. Comparing the calculated chi square with the table value, that is chi square calculated is less than chi square tabulated, and we accept the hypothesis and conclude that shading has no effect on yielding capacity of the. Now we conclude the results here. Example of 2 by 3 contingency table. If we are given a contingency table of 2 by 3, if there are two attributes or having 4 or 2 by 4 contingency table, there are 4 conditions or 4 classes. In this situation, we can't use this 2 by 2 contingency table formula, that is chi square is equal to AD minus BC square up into n upon R1 R2 C1 C2, and now in this condition we follow the we obtain the expected value of the each cell value by the formula, that is R1 and C1 row total multiplied by C total divided by total values. Expected value of 86 is equal to R1, that is 200 into C1, that is 126 divided by 300. Means if we want to find out the expected frequency of any cell, we take the total of that row and total of that column in which that particular value belongs and divided by the total number of observations. For instance, we want to calculate the expected value of 60. 60 belongs to row R1 and 60 belongs to column C2, that is R1 C2, means 200 into 93 divided by total frequency, that is 300, that will be the expected frequency of 60. Establish first null hypothesis. The sampling technique adopted by the two researchers are independent, and expected frequency of 86, that is it belongs in column 1 and row 1, that is column 1 total is 126, row 1 total is 200 divided by 300, that is 126 divided into 200 divided by 300, that is 84, and expected frequency of 60 the column total is 93 multiplied by row total is 200 divided by 300, that is 93 into 200 divided by 300, that is 62. Expected frequency of 69 we may find out by expected frequency of 44, that is 69 into 200. 44, expected frequency of 44, that comes in column C3 and row R1, that is C3 into R1, that is 69 into 200 divided by 300, and the expected frequency of 44 is 46. The remaining frequency we can obtain by the subtracting of that values, and like that these are the 84, 62 and 46 are the expected frequencies. Here total is 200, then subtracting the 192 sum of these 84, 62 and 146, that is 192, and we get the 8 after subtracting 192 from 200, then we get 8 here. Here total frequencies are 126. After subtracting 84 from 126, we get 42 remaining frequency. This is the expected frequency, and this is the column total is 93. After subtracting 62 from this 93, we get the 31 residual frequency of this value, we say that is the 33, and the third expected frequency of 25 is while we subtracting 46 from 69. This is the column total and this is the first frequency. If we expected frequency, if we subtract this 46 from 69, we get the balance frequency 23 here. And here total frequency is 12, and if we subtract 12 from 8, we get the remaining frequency 8 here. Here we see that this cell frequency is less than 4. If the cell frequency is less than 4, then we have to add this frequency or club the frequency of nearby frequency, so that we club these frequencies expected and observed frequency 23 plus 4 and 25 plus 2 during the calculation. Let us calculate the put the observed frequency here and expected frequency here. 86 having expected frequency 84, 60 having 62, 44 having expected frequency 46, 10 having 8, 40 having 42, and 33 having 31. And here we club the two frequencies 25 and 2 as a 27 and 23 plus 4 as a 27. First, we take the difference of observed and expected frequency, that is 86 minus 84 is 2, 60 minus 62 minus 2, 44 minus 46 is minus 2, 10 minus 8 is 2, 40 minus 42 is minus 2, 33 minus 31 is 2, and 27 minus 27 is 0. O minus E square, that is 2 square is 4, 2 square is 4, minus 2 square is 4, 2 square is 4, minus 2 square is 4, and 2 square is again 4, divided by the corresponding expected frequencies. O minus E square divided by E, that is 4 divided by 84, that is 0.048, 4 divided 62, that is 0.064, 4 divided by 46, that is 0.087, 4 divided by 8, that is 0.5, 4 divided by 42, that is 0.095, and 4 divided by 31, that is 0.139. Then sum of this summation of OI minus EI square upon E, that is 0.93, that is total chi-square value is 0.923. This is the chi-square calculated or chi-square observed. The expected frequency or tabulated frequency, that is with 4 minus 1 into 2 minus 1, that is 3 minus 1, 2 degree of freedom, because 4 minus 1 is 3 and 2 minus 1 is 1, 3, and again we subtract 1 degree of freedom. We have loss of 1 degree of freedom by summing of two frequencies 25 to 2. That we also lost 1 degree of freedom here, that is 3 minus 1, then the 2 degree of freedom, and that is 5.991. Inference we draw from these calculated and table value. Here the calculated value of chi-square is 0.923 and tabulated value is 5.991. That is chi-square calculated is less than chi-square tabulated, and we accept that the null hypothesis at 5% level of significance, and we conclude that the sampling technique adopted by two investigators do not differ significantly. Their sampling technique adopted by both the investigator are similar. 8th correction. In 2 by 2 contingency table, the number of degree of freedom is 2 minus 1 and 2 minus 1, that is row degrees of freedom are again there are 2 rows and 2 columns, and the degree of freedom r minus 1 is 2 minus 1 is 1 into column minus 1, that is 2 minus 1, that is 1 degree of freedom. If any one of expected cell having frequency less than 5, then we use a pooling method of chi-square test results with 0 degree of freedom, because we lost the degree of freedom by 1 pooling both the frequencies. In that case, we apply a correction due to ETS, which is usually known as ETS correction for continuity. ETS correction consists of the following steps. First one, add 0.5 to the cell frequency which is having cell frequency less than 5, and adjust the remaining cell frequency in such a way the row and column total should not be disturbed. And it can be shown that this correction will result in the formula, and chi-square is equal to n into mod of AD minus BC minus n by 2 whole square divided by a plus b into c plus d plus a plus c into b plus d, that is r n into mod of AD minus BC minus n by 2 whole square r1 r2 c1 c2. Example of its correction. In an experiment on effect of growth regulator on fruit setting in muskmelon, the following results were obtained. Test whether the fruit setting in muskmelon and the application of growth regulator are independent at 1% level of significance. These are the treated muskmelons and these are the control, and these are the fruit set in treated conditions are 16, while in control there are 4. Fruit not set in treated are 9 and fruit not set in control are 21. Total fruit set are 20 and fruit not set are 30, while treated having some 25 and control having 25. There are 50 total number of plants. And to solve this problem, first we establish the null hypothesis that 0 says fruit setting in muskmelon does not depend on the application of growth regulator, and alternative hypothesis fruit setting in muskmelon depend on the application of growth regulator. And the level of significance we used here is 1% level of significance, and we make the edge correction. Here we see that the cell frequency, that is control fruit set having only 4 which is less than 5. To increase the cell frequency as its suggested the correction, we have to add 0.5 here. That 4.5 become 4.5. After adding 0.5 in 4, that is 4.5. If this becomes 4.5, then we have to subtract 0.5 from 16, and 16 become 15.5. Then our first column total will be unaffected. If we take here 15.5, our column total increased by 0.5, so that we subtract 0.5 from 9, that is we 8.5, because our column total is 24.5. 9 plus 15.5, that is 24.5, and we add 0.5 to 9, then 9 become 9.5, and 9.5 plus 15.5, that is 25. Now this 21, we have to subtract 0.5 to balance these row and column totals, and 21 become 20.5, so that the row total is 25 and column total is 30. So that we, without affecting the row totals and this column total, we make the edge correction, and this is known as the edge correction. Edge correction is done when the one of the frequencies which one is less than 5, and here 4 is less than 5, so that we make the edge correction, and edge suggested that correction we have to add 0.5 without affecting the row totals and column totals in the frequency which is having less than 5 frequency. We already met. We use the test statistic chi square is equal to n into mod of AD minus BC minus n by 2 square upon a plus b c plus d a plus c into b plus d, putting the value of a b c d n into these, and n is 50 and AD 15.5 into 20.5, 15.5 into 20.5 minus 4.5 into 9.5, and row totals are 25, column totals are 20 and 30, that is 8.33. This is the calculated chi square, and tabulated chi square at 1 degree of freedom, that is 2 rows, that is 1, and column are 2, that is 1 into 1, that is 1 degree of freedom, is 6.63 at 1% level of significance. And here we see that the calculated value of chi square is less than the table value. Here we see that the calculated chi square is greater than table value, and we reject the null hypothesis, and we conclude that the fruit setting in muskmelon is influenced by the growth regulator. Application of growth regulator will certainly increase fruit setting in muskmelon. This is the conclusion. Conditions for validity of chi square test. chi वर्ग परीक्षण के लिए आवश्यक प्रतिबंध. The simple observations should be independent. Constant on cell frequencies, if any, should be linear, and the total frequency should reasonably be large, say greater than 50. No theoretical cell frequency should be less than 5. These are the limitations of chi-square. Application of chi-square to test the goodness of it, to test the independence of attributes, for declaration of linkage in breeding problem, to test for equality of many variances, to test the homogeneity of independent estimate of population variances. Properties of chi-square distribution. The mean of chi-square distribution is equal to the number of degrees of freedom n. The variance of chi-square distribution is equal to 2n. The median of chi-square distribution divides the area of the curve in two equal parts and each part being 0.5. It's a non-parametric test. The mode of chi-square distribution is equal to n minus 2. Since chi-square value is always positive, the chi-square curve is always positively skewed. Since chi-square values increase with the increase in the degree of freedom, there is a new chi-square distribution with every increase in number of degrees of freedom. The lowest value of chi-square is 0 and the highest value is infinity. That is chi-square is always greater than 0, and chi-square lies between 0 and up to infinity. Thanks dear.